How are you everyone? Today's lesson is factors affecting air spectrum. There are different factors that affect the spectrum of infrared radiation. From these factors that affect the position of absorbance or wave number, and also intensity of the absorbance or the amplitude of the absorbance, and the shape of absorbance that are affected by different factors. In the next slide, position of absorbance or wave number that affected by different factors that are energy required for absorbance. That means directly related to the absorbance or the frequency of the radiation. The intensity of the absorbance are related to the dipole moment of the bond, and the shape of absorbance are related to the broad or sharp peak and the information about the type of bond. Factors that affect the position of absorbed band are different from this. The amount of energy required to stretch the bond depends upon the strength of the bond and the mass of the bonded atoms. This is tested by Hooke's law. The strength of the bond affects the energy required to the stretching of the bond that between the bond. The longer the bond, the greater the energy required to stretch. That means it is directly related to the frequency of the vibration. As the bond between the bonding atoms increase, the energy required to stretch because of this shifts to the higher frequency or wave number. Frequency of the vibration is inversely related to the mass of the atoms attached to the spring. That means the heavier the atom vibrate at lower frequencies. That means when the interacting atoms are heavier or having large mass, their frequency, the vibrational frequency of these atoms or these bonds are also inversely related to this, and as a result decrease the vibrational frequency of that atom. Approximate wave number of an observation can be calculated from the equation derived from Hooke's law and describes motion of vibrating atom. Wave number is equal to 1 over 2 mu or reduced mass. C is the speed of light. As we see from this equation, wave number is inversely related to the mass of the interacting atom. As the mass of the interacting atom increases, the frequency or the wave number of the bond that between these atoms becomes, because it is inversely related to the frequency or the mass of the interacting atom. When we come to the force constant, wave number is directly related to the force constant of the interacting atom. When the force constant is increased, the frequency or the vibration of the interacting atom also increase. These equations clarify the relation between the frequency and the force constant, and also the mass of the atoms that are interacted with each other. As the force constant increase, the frequency or the wave number of the air radiation increase, and it is inversely related to the as we see, double bond is more stiffer than single bond, and also triple bond is more stiffer than double bond. That means they have more require more force constant or stiffer than double bond. As a result, the frequency of vibration also increase. Slide double bond is greater, triple bond greater than double bond greater than single bonds were based on force constant. And when you come to the mass of reduced mass of the interacting atom, chlorine carbon hydrogen bond greater than carbon carbon double bond greater than carbon oxygen bond greater than carbon chlorine bond and greater than carbon bromine and carbon have larger molecular weight. This results decrease in the frequency or the vibration of the frequency, and carbon hydrogen have low molecular weight and increasing in force constant or the frequency of the vibration. As a result, when connects the carbon atom with more electronegativity and having larger molecular weight, the frequency of the vibration also decrease, because mass of the interacting atom is inversely related to the wave number or the frequency of the vibration. By this formula we can calculate the average or approximate wave number of different bonds that have between the interacting atom. Frequency of normal modes of vibration of two at the mass of the two vibrating atom, as we can see in the previous slide. As the mass of the two vibrating atom increase, the frequency of the vibration decrease, and also depends the force constants of the bond between them and the bond order. That means the relative stiffness of the bond. As the bond stiffness increase, the frequency will increase, which increasing bond strength and bond order, and the frequency of the vibrating atom also increase by decreasing the mass of the interacting atom. Triple bonds are stiffer or vibrate at higher frequency than double bonds, and double bonds are stiffer than single bond. As a result, triple bonds are more have a frequency than double bond, and double bond are have more frequency than that of single bond. As you can see this picture, hydrogen has 2 gram per mole of molecular weight, and iodine have 250. The greater the mass, the lower the wave number, because wave number is inversely related to the frequency of the vibrating atom, because iodine has a larger molecular weight than that of hydrogen. As a result, the frequency or the wave number of iodine has much is lower than that of hydrogen, because the molecular weight of iodine is higher, because molecular weight or mass of the interacting atom is greater. As a result, the frequency of or the wave number of the interacting atom are much lower. For example, carbon-carbon bond stretching. The stronger the bond absorbs at higher frequency, as we said in the previous slide. Carbon-carbon triple bond are stiffer than that of carbon-carbon double bond, and carbon-carbon double bond are stiffer than that of carbon-carbon single bond. As we can see from this, carbon-carbon triple bond absorb or frequency having 2200 per centimeter, and carbon-carbon double bond having a frequency of 1660 per centimeter, and carbon-carbon single bond having 1200 per centimeter wave number or frequency, because carbon-carbon triple bond have stiffer and require greater energy and greater frequency. Because of this, the wave number or the frequency of carbon-carbon double bond is much greater than that of carbon-carbon double bond, and also the carbon-carbon double bond are more stiffer than that of carbon-carbon single bond, that have lower wave number or frequency that of the carbon-carbon double bond, 1200 per centimeter. Number range of 1640 up to 1680 per centimeter. This carbon-carbon double bond, when we come when we conjugate this carbon-carbon double bond, the frequency or the wave number of this interacting atom decreased at some instance from 60-40 or to 60-80 decreased to 60-20 up to 60-40. This is because of the conjugation of the carbon-carbon double bond. Another aromatic carbon-carbon bond, because this is more conjugated than that of a single carbon-carbon conjugated bond, approximately having a frequency of 60 per centimeter. As you can see, this the isolated carbon-carbon double bond have higher wave number or frequency. The carbon-carbon double bond are more or less than that of conjugated carbon-carbon double bond. This results lower in the frequency of the two vibrating atom. Another stretching bond has affects the force constant. That means as the S character increase, the frequency or the wave number of the interacting atom also increase. As we can see from this, SCP greater than SCP2 greater than SCP3, because the S character of has 50% of S character and 50% of P character, and as we can see from SCP2, 10.5, 1/3 of the hybridization has SC character, and 2/3 of that of the P character, and SCP3 has also decrease S character. As a result, the frequency of the vibration decrease from SCP up to SCP3, because SCP character are increased in SCP because 50% of sharing of the hybridization. Bonds with more S character absorb at higher frequency and higher wave number. SCP3 CH stretch just below to 2900 per centimeter, and SCP2 CH stretch just below just above 3100 per centimeter, and SCP character or CH stretch at 3300. As S character increase, the frequency of the vibration also increase, as we said before. Bending motion occur at lower energy or lower frequency than that of the typical stretching motion, because the lower value of bending force constants. Stretching vibration requires higher energy than that of bending stretching. Because of this, bending stretching absorb energy at lower frequency. For example, CH stretching frequency of or a wave number of 3000 per centimeter, and CH stretch bending vibration that absorb a frequency or a wave number of range 30 of the interacting atom becomes long. As a result, the frequency shifts to lower wave number. Slightly depends upon also the other atoms attack. The attacked atom have effects of resonance and inductive effect. Resonance also affects the strength and length of bond, and hence the force, its force constant. That means, for example, normal ketone has its carbon and oxygen double bond at as a ketone that is conjugated with carbon double bond near 1675 to 1680 per centimeter because of resonance effect. The resonance effect affects the bond length and bond strength, and also the resonance has the effect of reducing the force constant, and absorption moves to the lower frequency. As the resonance occurs, the frequency force constant decrease, and the absorption moves to the lower frequency, because force constant is directly related to the frequency of the vibration or the wave number of the vibration, because as the force constant decrease, the frequency or the vibrational wave number also decrease. This shifts to the lower frequency. As we see in this picture, two pentanone have there is no conjugation. As a result, the carbonyl carbon double bond to oxygen at observed frequency at 17-20 centimeter. When we come to 2-cyclohexanone, there is a conjugation with that of the carbonyl oxygen double bond. As a result, the carbonyl carbon oxygen double bond absorb frequency at 16-80 per centimeter. This is because of the resonance effect. 2-cyclohexanone, this result lowers the frequency to the lower wavelength. Carbon oxygen bond shows a stretch between 1250 up to 1050 per centimeter. If the carbon oxygen bond is in the end of the range, that means to the 1050 per centimeter frequency or wave number. If, however, the carbon oxygen bond is in carboxylic acid, the stretch will occur at the higher end of the range. Esters shows carbon oxygen stretch at both into carbon oxygen single bond. This results shifting to the both ends that have to the higher end and to the lower end. That means 1250 30-50 per centimeter. As we can from this diagram, or having carbon oxygen stretching that have a frequency of 10-50 per centimeter, because to the lower ends of the absorbing frequency. When you come to ether, there are two carbon oxygen stretching. This results to the lower end of the vibrational frequencies, and also carboxylic acid to the higher end of the vibrational frequency, because there is increase the single bond changes to partially single bond and partially double bond, because of the lone pair of electrons that have in oxygen that shifts to the carbon, and the carbon oxygen partially negative. As a result, the carbon oxygen single bond shifts to partial single bond and partial double bond. As a result, the stiffness of the bond is slightly greater than that of single bond. This results the vibrational frequency of bond in carboxylic acid shifts to the higher end of the vibrational frequency, that of 12-15 per centimeter. The other position of the frequency is the electronegativity of two vibrating atoms, or the mass of dipole moment effect. For example, carbon hydrogen single bond has a vibrational frequency of 2850 to 2960 per centimeter, and nitrogen hydrogen stretching bond having the frequency of 3300 up to 3500 per centimeter, and oxygen hydrogen having a vibrational frequency of 3590 up to 3650. This, as you can see from carbon hydrogen to as we can move from carbon hydrogen stretching bond to oxygen hydrogen bond, the electronegativity of carbon is less than that of nitrogen, and the electronegativity of nitrogen is less than that of oxygen. As a result, the electronegativity of the oxygen is greater than that of nitrogen. As electronegativity of the interacting atom increase, the dipole moment also increase. As the dipole moment increase, the frequency of the vibration also increase. This is due to the electronegativity of vibrating atom. Electronegativity increases the dipole moments of the interacting atom. As a result, the vibrational frequency of the interacting atom also shifts to the higher frequency. As carbon-carbon single bond around 1250 per centimeter, and carbon-carbon nitrogen single bond stretching around 1350, and carbon oxygen around 4000 per centimeter. This is because oxygen is more electronegative than that of nitrogen, and more electronegative that of carbon. As a result, the vibrational frequency shifts to the higher frequency that of carbon-carbon double bond. And carbon-carbon double bond has a vibrational frequency of the 1620 up to 1680 per centimeter, and carbon-nitrogen double bond has a vibrational frequency 6020 up to 6090 centimeter per centimeter, and carbon-oxygen carbonyl group that have a 1780 per centimeter. This is because of also the electronegativity, and this results the increasement of dipole moment. As the dipole moment increase, the vibrational frequency of the interacting atom also increase. As we can see from the introduction part, the elements that or functional groups that absorb IR radiation when there is the difference in electronegativity, or there is a change in dipole moment, and the IR radiation that have sufficient energy to shift the ground state of the vibrational state to the excited state or higher energy level of the vibrational state. When these two rules are confirmed, there is absorption of IR radiation. Factors that affect the intensity of absorption bands, or is there a strong or medium or weak absorption band or intensity? There are different factors that affect this phenomena. In the dipole moment associated with the vibration, as the charge of the interacting atom or the increase, the dipole moment also increase. As the dipole moment increase, the more intense the absorption. That means the greater the change in dipole moment, the more intense the absorption, because the charge of the interacting atom increase, the dipole moment also increase, because dipole moment is equals to charge of the interacting atom times the distance between that of the interacting atom. For example, oxygen hydrogen bond versus nitrogen hydrogen bond, and nitrogen hydrogen bond versus carbon hydrogen bond. Oxygen hydrogen bond has more polar. That means there is higher electronegativity and dipole moment having more intense, and nitrogen and hydrogen bond having medium intensity between that of carbon and hydrogen. As a result, there is higher dipole moment within the interacting atom. The greater the more the intense the absorption, and having larger dipole moment. The intensity of an absorption band also depends on the number of bonds responsible for the absorption. The first factor that affects the intensity of the absorption band is the dipole moment of, or the charge that the interacting atom have, and the second is the intensity of absorption depends on the number of bonds responsible for absorption. Having 70 carbon hydrogen bonds that have 17 carbon hydrogen bond or molecules that absorb IR radiation versus we have 3 carbon hydrogen bond. As the number of bonds responsible for absorption increase, the intensity of the absorption also increase, because 70 carbon hydrogen bonds have more intensity than that of 3 carbon hydrogen bonds. The concentration of the sample used to obtain IR radiation or spectrum also affects the intensity of the absorption band. Concentrated samples have therefore more intense absorption band. That means there are large number of bonds responsible for the absorption of IR spectrum. as a result, like that of octyl iodide that have 17 carbon hydrogen bonds, the more the intensity of the absorption than that of methyl iodide that have 3 carbon hydrogen stretching bond. And concentrated samples have greater number of absorbing molecules or bonds, therefore more intense absorption band increases. Therefore, the concentration is directly related to the intensity of number of molecular number of bonds responsible for the absorption increase. The intensity of the absorption band also increase as the charge of the interacting atom increase and also the dipole moment of the interacting atom increase. The intensity of the absorption band also increase. As we can see from this diagram, there is S is strong absorption band and medium and weak absorption band. This because of the dipole moment of the interacting atom and also the number of bonds responsible for for the absorption of IR spectrum, and also the concentration of the absorbing analyte or compound. Generally, as the dipole moment increase or the charge of the interacting atom increase, the intensity of the absorption also increase, and the number of bonds responsible for IR spectrum increase, and also the frequency of the vibration or the intensity of the absorption band increase, and the concentration of the compounds that are responsible for absorption of IR spectrum or radiation increase, the intensity of the spectrum also increase. The other factor is hydrogen bonding. These factors are affecting the frequency shift and the shape of the spectrum. Hydrogen bond alters both stretching and bending vibration. In stretching vibration, causes vibration to move to the lower frequency. That means the frequency of the vibration decreases to some extent to the lower shift or the lower frequency, and too long. That means two longer wavelengths with increased intensity. The intensity may not decrease or that is increased, and the frequency is moved to the lower frequency, and the wavelength moves to the higher frequency wavelengths, because as the frequency decreases, the wavelength is also, and wavelengths are inversely related to each other. And hydrogen bonding causes band widening in stretching vibration, but hydrogen bonding in bending vibration higher frequency, because as we said before, frequency and wavelengths are inversely related to each other, less pronounced than that of stretching vibration, because bending vibration have require less energy to vibrate the bending,